our speaker today really does not need any introduction, I think. Frédéric Barlat is a very well-known name in the field of material forming, in the field of plasticity and constitutive behavior, and so on. And he is also a very well-known name, for an important name for our association, since Frédéric Barlat has been one of the members of the board of directors for several years. And, you know, he gave to the association very important contributions and support. Nevertheless, I would like just to provide some notes briefly from his bio sketch, because I think that they could be very inspiring for young researchers that are connected here. And so just, you know, very briefly, let me recall that Frédéric Barlat received his PhD in mechanics from the Grenoble Institute of Technology, and just before moving to Alcoa Technical Center in the US near Pittsburgh, Pennsylvania. He worked there for more or less 20 years, and then he moved to the Republic of Korea, where he joined the Pohang University of Science and Technology as a full professor. He is currently an emeritus professor at PostTech, but also invited researcher at the University of South Brittany in France, and visiting professor at the Institute of Global Innovation Research at the Tokyo University of Agriculture and Technology since 2016. Over his career, Frédéric Barlat published more or less 300 articles in scientific journals and book chapters, you know, concerning innovative plasticity theories and, other works related to manufacturing technologies for metal products. And of course, he also received several prestigious awards. Let me just recall the Cannes International Award for Outstanding Lifelong Contribution to the field of plasticity. Very impressive. Congratulations, Fred. So his webinar today will be focused on isotropic and anisotropic plasticity under isotropic hardening and anisotropic hardening, but also putting some emphasis on distortional plasticity, and giving us also some details about finite element implementation and some simulations and so on. So it will be a very exciting presentation. Let me recall that after the presentation, we will have some minutes for some questions and answers. So after the presentation, all the participants, feel free to raise your hand, switch your mic on, and raise your question. Or if you prefer, you can simply type your question in the chat, and I will read it for our lecturer. And in case, feel free also to write your affiliation in the chat, just, you know, to get in touch with others. As our president was saying before, ISAFORM is much more than a conference. We are a community. We would like to create new networks and to stay in touch. So if you would like to introduce yourself briefly there with your affiliation and interest, it will be great. So that's it from my side. I think we can start with the real presentation. So Fred, whenever you are ready, you can share your presentation, and please, the stage is yours.
Okay, thank you, Piero. Do you hear me?
Yes, clear and loud.
Great. Thanks, Katia, also, and all ISAFORM organization. And it's an honor for me to to give a presentation this afternoon. So let me check if I share. Okay, do you see my presentation?
Yes, it is there. Feel free to start.
Okay. I want to. Okay. Okay. So let's start. So I'm going to talk about isotropic and anisotropic plasticities. It's really my main work topic, plasticity. But of course, when we do plasticity, it's to apply it to something which is, in this case, forming. And so let's go to first, to the outline. So I will give a little bit of background. Trying to start, look at the 510, okay. Some talking about conventional plasticity first, then I will extend to anisotropic plasticity, distortional plasticity, finite element implementation, and some conclusion. So as a background, just this one on sheet metal forming. So this is a sketch of a forming process. And of course, we need, if we want to do forming, we need some equipment and something like a press. This one is a small one. This is the one we had in a postdoc in my lab. But industrial press are much bigger than this one. But just to say that, and you all know that because we are at ESAFORM, that it's very complex to look at the forming process, and there are multiple parameters to control, such as machinery, tooling, geometry, material, interface between tool and material, the scale. We can do something huge and something very small, and also environment can be temperature and so on. So there are many things of interest, and of course I cannot look at everything because I don't know everything, first, and second, I'm more interested in the material and the plastic behavior. So this is what I'm looking at that, and especially I'm going to look at, think about the new, not new material, but steel is not a new material, but the new steel we do right now, they're really very strong because we call them giga steel. So over 1 gigapascal strength and even 1.5 gigapascal. And I show this example of a rail here. And all those examples are coming from POSCO, which I thank for their support in the past. And when we want to design a process about 500 megapascal, it's quite difficult to do it just by, empirically by experience, and it's really difficult to do that without predictive tools. So what we do usually is do finite element simulation, and with this we do some optimization using finite element tool. And we can do forming. So for instance, the example of a B-pillar. So this is just the sketch with the finite element. But also for performance. And when I say performance, is like fatigue or crash performance, crash worthiness. So it requires a lot of simulation. And in all those type of simulation, the plasticity model is important. It's one of the important considerations. This is not the only one. As I mentioned before, there are many aspects, but at least plasticity is an important one. So therefore, I will talk about plasticity. But before, we can have this question that, do we need really constitutive model? Because with this AI coming now is developing very rapidly. Do we still need constitutive model? And so this slide was given to me by some German colleagues. Yes, it's a very nice tool, AI. But when we do design of a process, the problem, we don't have much data. If we design a process, we have virtually no data. So another way to do it is to do AI to generate a constitutive model and do very fast calculation based on that. The problem is we still need to train the model, and to train the model for a process we don't know yet because we are designing. Well, we need to have a material model, so we fit a material model to some kind of a network, a neural network or others, and then we can do the simulation very fast. But for the training, we still need to have constitutive model, and of course we need to have a constitutive model that can predict the real behavior as accurately as possible. So therefore, I think a constitutive model is still a very useful tool for the future even. So in terms of plasticity, we have plasticity and hardening. We have several scenarios which I represent schematically in a deviatoric plane. So we have isotropic hardening or kinematic hardening, and those are well-known models in plasticity. Or we have isotropic kinematic, which is a combination of both. Or we have distortional kinematic also, and distortional kinematic came also, I don't know, we would say in the 70s or 80s. But what we've been working more recently in the last 10 years or so is more distortional isotropic, and this has not been done before that. About 10 years ago, this is when or 15 years ago when we started. And well, I'll show you why we chose distortional isotropic rather than distortional kinematic. And so there are different scenarios, but usually what we do is because measuring yield surface is very tedious, and so it's necessary to do it. And we have specialists about this kind of topic, such as Professor Kuwabara in Japan, and we have others, of course, but I have a good working relationship with Professor Kuwabara, and it's very good we do it, but in terms of industrial application, it's difficult to do all the tests required, and it requires a lot of hard and very precise work that maybe industry is unable to do by themselves. So we assume one of the scenario I showed you and try to calibrate with a few experimental measures. So in terms of modeling, I cannot, of course, plasticity, it's full of a constitutive model, and I cannot, in one presentation like this, talk about all of them. But so I will start with von Mises isotropic. If we know the yield condition, which means it's an effective stress equal a reference stress, like a stress strain curve in tension, for instance, then this is all we have to define to know plasticity, especially if we assume an associated flow rule, which means the strain increment is normal to the yield surface. So when we have this equation, then we can do simulation, basically. I represented here with deviatoric stress, but in terms of normal stresses, we can write that this way. Now, material is rarely isotropic due to thermomechanical processing, like rolling and so on. And usually what we do in sheet metal forming or metal forming in general is to to use plastic anisotropy. And in case of Hill 1948, which is very well known, it's a change. It's a modification of von Mises with the coefficient I shown here in red on my presentation. The difference with von Mises is, beside those coefficients, is that we need a material-based reference axis. Okay, we cannot take any reference base vector, any set of base vector as we would do with von Mises, but we need a reference frame attached to the material, like rolling and transverse direction and normal direction in sheet. Okay, but non-quadratic plasticity model were suggested by crystal plasticity. And so this is the reason new, which they are not new anymore, but non-quadratic model were developed. And of course, there are many other after that, but many of them are based on this one or using the same method as this one. So on the two I mentioned, there is a plane stress yield condition or effective stress with 8 anisotropic coefficients. And there's a 3D model which has 16 independent coefficients. But out of the 16, actually there are 18 coefficients, but 16 only are independent. Now we can always use a 3D model plane like 2004 can be reduced to plane stress. Okay, if you set 3 of the stresses to 0, then it reduced to plane stress, but it's different than the 2D model because we have more coefficients, and more coefficients means we have more accuracy in the description. I mentioned already we have other model, but and I want to talk about an example. It was done some time ago with using stack sheet specimen. When we take a stack of sheet specimen glued together and we do a biaxial compression, we can describe a yield condition in principle in 3 directions, but usually mostly in 2D, as I represented here for an aluminum magnesium, 2.5% magnesium. So here we have the experimental results are shown with a symbol, circle. And we have a simulation, polycrystal simulation in dashed line, which we don't see with a solid line. The solid line is a constitutive model, the continuum model. And you see, of course, there's a fit with all those experimental data, but for the continuum model, it's fitted with the data, but the Taylor, Bishop, and Hill, the crystal plasticity model, is done with the texture. But you see that all those 3 approaches, experiments, crystal plasticity, and the constitutive model, 2004, they are all giving something like a rugby ball. Okay, it's not like an ellipse, like a hill. And of course, we need to do that in 3D. Okay, so with the experiment I showed you, of course, we can build a 2D model, and we have to do some other tests. Like there is one representing shear, but it's just projected here. We can get an extra point. And okay, the more point we get, basically, is the best. Okay, but sometimes we cannot do everything. So anyway, we need to define this 3D object with experiments, and very often we have only just a limited number of experimental data, and that's why the constitutive model must be accurate. I mean, must be follow the plasticity constraint. And we can, using this, so I will show another example where we do tension in different direction, 0, 45, 90, but others also 50 and so on. We can measure the flow stress from a tensile specimen, but also the ratio of the width to thickness strain, so the so-called R value in axial tension. And this is done on the aluminium 2090 T3. This is an aluminium lithium alloy, which was developed by Alcoa when I was working in Alcoa. So the black line, dash line, represents the curve, the anisotropy curve of the flow stress with a scale on the left side in black also. And all those points are the experimental points measured every 15 degrees. Now the red curve represents the R value, this strain ratio, and the square symbol. And you see that with this yield condition, we are able to represent the plastic behavior quite well. Of course, this is a fit here, okay? I don't pretend this is a prediction. This is a fit, but the thing is that with Hill 48, for instance, it's impossible to do such a good fit. And so that's why it's important to get the right model. Okay, also I just saw here the yield function. What did I put here? Okay, oops, sorry. Anyway, this is a 3D yield function. The 2D model would give still a good agreement, but not with the detail that we see here, because the 2D model would take only 3 points at 0, 45, and 90 degree, 3 points for yield stress, and 3 points for R value as data to identify the model. So this was, I would say, conventional plasticity. Now I will talk about anisotropic hardening, because in forming processes, the strain paths are not linear. And the strain paths usually are changing. Especially in multi-step forming operation, but even in a single operation, strain paths are changing during plastic deformation. So this is a sketch of a non-linear strain path. So they can be curved, they can be linear by steps. So you may have one step here and a second one here. And then you can have 2, 3, 4 steps. Now, if you do this one, you can go up to this point and come back. This is reversal. So many non-linearity with different pre-strain or even curve strain pass, and everything can be mixed together. So hardening is really not very simple in this type of nonlinear strain path case. So, and those nonlinear strain paths induce some change in hardening. So I showed here a true stress strain curve with the isotropic hardening, the conventional hardening curve. But if we do some pre-strain and reload, we may do some reverse loading. We'll get the Bochinger effect in red here. Or we can do cross-loading. Cross-loading being, for instance, tension followed by tension at 45 at, let's say, 60 degrees. But it can be other possibility like tension followed by simple shear and so on. So, and with cross-loading, we can reload at a lower stress, a little bit like Bochinger effect, and then recover the stress strain curve. Or we can overshoot the monotonic curve like here. And one thing I forgot to mention is the Bochinger effect. Not only we reload at a lower stress, but usually we get some kind of permanent softening that the new curve never recovered the level of the isotropic hardening curve. So we can get all those effects. And to represent that, actually, because we cannot do all possible case of strain path change, then we have to rely on a few change only and assume the model is accurate enough to represent all that. So the most difficult, of course, is for multi-axial stress states. Here I represented the effect in a uniaxial stress state, but what happened in a multi-axial stress state, and it's more complex. So I want to look at an example that's taken out of Professor Kuwabara, not Professor Kuwabara, sorry, Professor Kubara, sorry, Tozawa, I'm sorry about that. It's about plane strain compression, biaxial compression, as I showed you before, stack sheet specimen. And what happens is this example is that it's brass. And the first step was rolling. It follows this purple curve here. Then unload, and then reloading in different direction to probe the new yield surface. And this is done after different pre-strain, after different offset strain, like the first curve represent here at 2 10 to the minus 3. Okay, and of course, if you do lower strain, this is more engineering definition of a strain, but if you reload at lower strain, you can get very distorted yield surface, and it's becoming very complicated. Also between 0 and 0.002, it's very small amount of strain. So is it really necessary to take this into account? I think so, but I don't think so, but this is my opinion. And also what I think is that offset strain in the order of 10⁻⁵ or 10⁻⁴, it's nonlinear, and therefore we can say, yeah, we have plasticity, but it could be also as well viscoelasticity. So to me, it's not clear-cut enough that we have plasticity in these ranges. We have certainly, but I'm not sure the measurement is reliable or not. So anyway, when I talk about yielding, I'm always talking about this kind of offset strain that around 10 to the minus 3. So we see that we have some distortion of the yield surface, in particular, some kind of flattening at the direction opposite to the former loading restraint. And if we increase the strain, then we see that we tend to recover a more regular shape. Although at 3%, it's not completely recovered, because this is the same length I had on the other side here. Let's say after 5%, maybe we recover almost everything. So those changes there are fluctuations that are temporary. Okay, it's not it doesn't stay completely like that. But anyway, it's changed the behavior of the material for at least 5%. And I would say here I see more distortion than a translation, and there can be some translation of the yield surface, but yeah, it's difficult to say. So crystal plasticity, if we do crystal plasticity together with directional dislocation, density accumulation, so the regular crystal plasticity model is not going to show you what I'm going to show you. You have to have the interaction between dislocation to capture this, but what you get is something like this. That this is just a linear strain path, okay? But to show that when we do a linear strain path, like pulling in this direction, and here it's uniaxial tension in this direction, the yield locus is given by the yellow contour here. And we see the same thing as before. We see a flattening of the yield surface in the direction opposite to loading. So it's been something that we observe also in many work reported, that we get some flattening of the yield surface in the direction opposite to loading. But I show you two examples where one is experimental, the other is more model based on crystal plasticity. So it looks like a distortion is a good model to describe this. And this is the reason why we decided to go this way, only distortional, and only distortional because to try to simplify, if a material model is too complicated, it's very difficult to use in practical application. And that's why we try to remain as simple as possible, although when we start to have nonlinear strain path, it cannot be that simple. Okay, so I will now go directly to distortional hardening. Distortional hardening is anisotropic hardening, okay, but I'm just making this distinction just because I'm going to talk about this distortional only, no kinematic hardening. So I start with a yield condition of the same type as isotropic hardening, which means effective stress. Here I have 0. Effective stress to the power Q, and then 1 over Q equal reference flow stress. So basically, it's an effective stress equal a reference flow stress. This is isotropic hardening, even if this function is an isotropic yield function. And this would be in a pi plane. Again, it would be the solid line. If it's normalized, and it would be always this solid black line here. But actually, this is actually the yield or the effective stress, but the effective stress is actually this chi bar, C bar is extended to allow the some cross effect. So if you look at the figure, the dashed line, it would be some kind of contraction that occurs during loading in this direction. So loading in this direction, the loading is S, and I have another tensor here, which I write H, and it represents the microstructure that I develop if I pull in this direction here. And so I'm going to get something like this with this. It's a linear transformation, actually, I do. And we get something like this. But if I add an isotropic state variable, G here, and another function, which I will show after, then I will create a distortion in the direction opposite to loading. So I'm going to truncate this. This is the same I truncate in this location here. And I'm going to have this dashed line, which represents the final distorted yield surface with, again, the microstructure deviator representing the direction of the loading, the first loading. And this deviator is going to move, and I will show you how. Of course, we have also other state variables here, like F1, F2, and others that are hidden, but we need more variable to describe this type of new yield surface shape. And actually, if I want to do some change, so I'm going to change. Okay, I was loading in this direction here. Now I'm loading at it's cross-loading here, cross-loading, pure cross-loading, because it's 90 degrees in a pipe plane. So the yield surface is going to rotate, and the microstructure deviator is going to rotate as well, because microstructure deviator tends to align itself with loading, but it cannot do instantly. Okay, it takes time to change a microstructure. So even if the loading is changed instantly, the microstructure will change, but gradually, and that's what this rotation tends to represent. Whether it happens like this in the reality, reality is very complicated. It's just a model, and this is just a way to try to express what happened. And we have several versions of what we call HH model. This isotropic distortional model on a dual phase steel. So we know T for tension and C for compression, and this one is TCT, means tension, compression, tension. So we have two curves here with different amplitude for the change. So one with a small amplitude, and the second one with a bigger amplitude here. And so with this, around the circle are the experiments. The red line is the model, and it works well. If we do transverse direction tension plus rolling direction tension, then again, we do some pre-strain. So the experiments on the pre-strain only are represented, the experiment here. This HH20, so the last version of HH model is capture the experiments quite well. The blue line was the former model, I mean the previous model, HH14, and we had a small problem here, and this is one of the reasons we try to improve to HH20. And the last curve is tension in transverse direction followed by tension at 45. And here you see both the model and both model actually. The 20 and 14 are both matching the experiments well. So with this model, we're able to represent a number of experiments, reverse loading, cross loading, and we expect that everything in between, it's either between cross-loading and monotonic loading, or between cross-loading and reverse loading. So it looks like we probably would be able to capture most of the possible loading. We can do also cycle here, and this was done on a martensitic steel with 1500 megapascal of ultimate tensile strength. And again, we have a good agreement with here. This is only one curve, okay? Tension, compression, tension, compression, tension. Again, we have a good agreement between the experiments and simulation. And here, this is aluminum alloy, and this is some kind of cycle plus tension. And the model represents this behavior quite well. Okay, so now I'm going to talk about still an approach based on isotropic distortional, but we call EXA, and it's the most recent model. It's a little bit like HH, but we don't have large rotation of the yield surface when we change strain path, as I showed you before. And one of the reasons is it's difficult to capture the coefficients correctly when we have this rotation. We notice that. And it's difficult to represent exactly what we want, because the rotation is kind of a difficult concept to handle. So what we do in this model HEXA is that we don't allow the rotation that are larger than a certain angle. If I represent here the pi plane again, I have the yield surface. If the pre-strain or the preload is in this direction, and if I'm loading close to the pre-strain, then I allow the rotation. But if I'm going to do a strain change, which is, let's say, in this direction, and this is the other plot here. In this case, I'm going to generate a new microstructure deviator. So I'm going to have two microstructure deviators here, one vertical and one horizontal. And if I change strain path again, and I will add more deviator, like H2, Hn, so we may have many deviator in principle if we do that. But only one is assumed to be active, which is the last one. And all the other one tends to recover the isotropic hardening stage, and actually they are removed when they don't contribute to the yield condition. So practically, we don't have so many microstructure deviator to handle at once. And also each microstructure deviator is defined with the same coefficients, maybe not the same not the same direction, but the coefficients to identify heat or to evolve it are similar. So we don't have too much difficulty. We don't have more coefficients. That's what I want to say. But the state variable evolution are similar than HH20. They had to be changed, of course, but the idea is the same as HH model. And as an example, I show you here with an HH model a case where we pull in the vertical direction here. It's a yellow, kind of yellowish curve, and then we are going to pull in this one. So the final is the dark one here. And we are going to start from, on purpose, I put this pink, which is the initial shape after the pre-strain. slightly tilted on the left. And at the end, it's going to be like this, the final strain path or final load. And this one is almost the same, except it's slightly tilted on the right. And I'm going to load in the same direction in the second path. But when you look at the shape, it's slightly different, very slightly. If you look at the bottom here, slightly different here, and the size of, because all those lines represent the evolution of the yield surface. So one line represents one evolution. So you see those lines here are more dark green, are more in this direction, whereas here they are a little bit different. And so it's kind of a singularity here. And this is the reason why EXA was developed, because we don't have this singularity. If you look at the two yield surface, this is the same example as the top row with EXA here. And we don't see any difference at all in the shapes. And I have some video to explain that. Usually, okay, let's see that. So here I'm going to compare HH14 and HH20. Okay, so you see that during the transition, the shape is not exactly the same, especially HH14, because actually one of the purpose of HH20 is to make the evolution more similar. But it cannot be similar exactly. And if I do that again, I will stop at some point. Okay, you see HH20 is more or less the same. Oops, this is not what I wanted to do. I wanted to go progressively. You see here now, we see that still HH20 is not exactly the same in its evolution. Oops, okay, sorry again, but okay, another time. Okay, but at the end, similar. Now, if I look at HH20 and EXA, so HH20 is here, EXA is there. Okay, this is what we see. And now, if you look at the bottom one, EXA, you will see the evolution is exactly the same. Okay, so we don't have the singularity anymore, and this is a good thing. Singularity is never good, especially mathematically speaking. So that's why we wanted to avoid this. And with EXA, we get also good simulation results. Here, this is the experiment gray line. So this is a few cycle, but it's only one curve here. And the simulation are in red. Now, one thing is this data was fitted manually with some trial and error. But what I want to say is we didn't need much effort to calculate the coefficients to get this red curve. If we want to be more accurate, maybe we can do better with some optimization tool, but at least this red one can be the initial estimate, initial curve, and in this case, we probably can do a good job with an optimization tool. Now, if we do pre-strain, like from tension in different direction, we see we get a good agreement again. And here, this is a case of when we have overshooting. We see that we are able to represent overshooting well. And also those examples where coefficients were calculated so-called manually. We just, because we know the coefficient, we know what they represent physically, and therefore we are able to calculate, I mean, to entreat them and to find a good agreement. So even if we have a good model, plasticity model, we need a good implementation if we want to get good results. And this is the purpose of this section. We need to integrate the stress. And there are many ways to do this. So basically, we have at a given step, we impose the next step, which is a total strain we impose. And we want to know what is the stress increment and the effective strain increment. So the most used method, most powerful method is closest point projection method, or CPPM. It's the most accurate, and basically it's Newton-Raphson. But this is a method that takes some time, and because we first assume we do a prediction using an increment that totally elastic, and then come back to iteratively to the solution. And this takes some time. And the reason we wanted to have something simpler and faster, maybe not as general as this method, which can be applied in many problems. This one is more specific. The one we developed is more specific to metal forming. And this is a non-iterative method, which indicated by his name is non-iterative because we use an elastoplastic predictor first. And this is represented by this. Okay, we just go directly to the solution. No, it has been done in the past, and it was not always very used in the literature, and maybe one reason it was not that accurate. I'm not sure, but in this formulation, actually, when we say it's non-iterative, but we have to do a projection. So we first find a stress update elastoplastic, and the problem is when we do that, we are not exactly on the yield surface. So we have to do a projection on the yield surface to get exactly the point and exactly the loading point. And the reason is if we are not at the loading point, and if we have many state variables that are limit, especially not in this model, we have the variables, they must be between limits, otherwise the problem is code is going to crash. And so in order to make sure that it is on the yield surface, we have to project the stress we found just before, project on the yield surface. And when we do this, we actually get a good integration. So just to show, of course, it's difficult to compare, but if we compare the two methods, so CPPM, fully implicit, and SPM is fully explicit because it's only one step. So this is the two methods, and we represented the stress in different elements, and I think it was a square cup this case. But if you look at the two, the stress that in both cases they are the same. Okay, maybe there's very small difference, and it's almost impossible to see where the difference is. And actually, when we do the simulation and represent simulation with those two methods, we get the same results. So an application to this method, non-iterative method with a S-ray, and I'm not going to present all the detail, but just the simulation time, but the results were almost the same. But simulation time with, so we have CPPM, okay, this is Newton-Raphson method. Here, non-iterative. Okay, you ignore the middle method. But for forming this non-iterative method is about half of the time of the forming. So 100 hours for CPPM and 52 hours for non-iterative method on the same computer. For Springback is about the same, but still we save a lot of time for the forming steps. And it was done with a Yoshida memory model, and we got about 50% change in a reduction in the time. We did this with a HH20, and we get about the same time reduction as well. So you just need to compare the red and the blue, because this is the only one I am talking about here. Okay, and application to a B-pillar, and here I'm just going to show just one result, because it's impossible to measure anything on this type of complex part, but just to show you that when we do the simulation, and so it's been done here with LS-DYNA, I think. We are able to, the part is quite complex, okay, and quite complex, and we have a lot of contact, and very often code they crash before finishing the simulation. But with this stress integration method, we are able to finish the simulation and get here, for instance, it was I didn't put the material, but the TRIP 1200. So we see that, of course, some stress sometimes is 1.4 gigapascal, because with some hardening. But anyway, we're able to finish the simulation. And here, this is just what we can do is look at whether the material had experienced some strain path change. For instance, between red is monotonic loading. When we have some blue, it's because we had reverse loading. And if you have some green, it's because not far before the end of the simulation, we had some cross-loading. Okay, now this, we have a UMAT, my student. He's not my student anymore, but my former student put all this model, and it includes those new integration method, but many different constitutive model, even some fracture model. And it's all available on this site. So I will leave you, if you're interested, I will leave this presentation, and you can copy you can check the website yourself. Okay, I hope I'm not too long. Well, I was a little bit too long, but anyway, sorry about that. So the conclusion, just so we observe that there is dependence of plasticity on the loading history, and with a model based on distortional plasticity only, without no back stress, we are able to represent the behavior quite well. I showed you several aspects of the microstructure that, like the texture or dislocation and so on. So physical understanding is important to develop the model at a continuum scale. And I think constitutive modeling of plasticity and the finite element implementation is still an active research topic. I think AI will be very useful, but I think it will be as a complement of quantitative model. I think quantitative model of plasticity is still very important in my view, and I hope you all will be interested in this topic. And I thank you very much for listening to me.
Thank you, Fred. It is us thanking you for guiding us in this journey through isotropic and anisotropic plasticity and all the details and all the theories that you showed us. It was very, very interesting, in particular, looking at what we can get, from some simulations implementing, all advanced modeling and, approaches. So thank you, really.
Thanks, Pio.
Maybe we have some questions from the audience. I can see more or less 100 participants still there. That is a very good number. So let me also check the chat. Can you read the chat? There is quite a long question.
The chat. Okay, maybe I need to stop sharing, maybe.
Or otherwise, I can read this for you. It is from Professor Adharan Krishnaswamy, IIT Madras, and he's saying one of the requirements of elastoplasticity is that the plastic work should increase continuously. In other words, the elastic energy should increase with deformation. Geometrically, elastic energy is the volume under the yield locus. How does distortion hardening ensures continuous increase in elastic energy during deformation?
Well, the elastic energy is one thing. Hello? Yes, elastic energy is one thing, but actually, the plastic energy is calculated the same as in isotropic hardening. So I think there is no problem with this. I mean, the model is developing at each step is consuming some plastic energy, positive plastic energy. So I don't see a problem here. Even if the stress is low, still in the next step we consume some energy. I don't know if this is the question. Okay, but
yeah, I see. Yeah, I mean, most probably, I think that Ari is interested in investigating a little bit more on this. He will stay in touch for sure.
Yeah,
so
I think it's probably the best way is to if my answer is not satisfying, then I can continue to chat with whoever is interested.
Okay, so several participants are saying thank you here. Great. And if there are more questions, please just switch the mic on and you can interact directly with our speaker. Yeah. Meanwhile, I have this curiosity, Fred. I'm not really, working on this, so I'm not the right person for raising very specific questions. I just, wanted to understand which is your feeling about the future of, simulation in order to have a very precise prediction. Which kind of model or constitutive modeling, hardening model we should consider.
Well,
looking at the ones that you do present, are they material sensitive? Pros and cons. Looking at different approaches.
Well, no matter what approach we do, it's a picture of it's a mimic of reality. Reality is very complex, and it's impossible to describe accurately what happens, the most accurately. Okay, but if you start from a very low scale, okay, maybe you can say I describe the physics better. Well, first, I don't think physics is a question of scale, because the theory of relativity is for the universe, and it's still physical, but it's not a question of scale.
I see.
So I would say microstructure is a more microstructural model. Is it better? Well, I'm not sure, because yes, you are smaller in scale, but there is physics in continuum. Okay, continuum is physics also. So I think model to describe what we do in plasticity, generally for forming, in my opinion, it's better to take it at the continuum scale, and knowing that we have a limitation in the continuum scale. Okay, but there is another important point I want to mention, is if we want to use the model commercially or in industry, it cannot be too complicated. Already, this kind of is already difficult for industry, I think. Even though some industry, in particular POSCO, I know they were interested. So if we start to use texture and dislocation, and it's going to be very difficult for analysts who are doing this kind of design to use. So there's we know that we are limited in terms of accuracy, but taking too much microstructure is not necessarily better. So there's always a balance we have to do between ease of use and what you want to describe, and there should be a balance. I mean, we cannot have both at the same time.
I agree. I completely agree with this consideration. Yes, completely right. So thank you again for your presentation and discussion, Fred. It was really our pleasure to have you, to host you here.
Thank you very much.
Such an interesting presentation. It was really an amazing journey